very much. So, so my name is Mathieu Bauchy from UCLA in California. And so I'd like to tell you about the work that we've been doing in predicting how atom moves in molecules or in matter in general. And so what we're interested in doing is this. So here this is a liquid, for example, and the atoms are moving over time. And so if we understand how the atoms are moving over time, then we can predict many properties about these types of materials. And so usually the way we predict how atoms move over time is by using molecular dynamics simulation, where, for example, you start with the position and the velocity of all the atoms, and then based on that, you can calculate the energy between all the pairs of atoms. And if you have the energy, then you can calculate the force as the gradient of the energy. And if you have the force, then you can calculate the acceleration with the Newton's law of motion. And then once you have the acceleration, you can calculate how the velocity and the position is changing after a small increment of time. So that's the typical algorithm of molecular dynamics that you can use to predict the position of the atoms as a function of time. And so the problem with that is two things. First, so the first thing is this: we don't always know this energy as a function of the position of the atoms. So if we don't know the energy, then we are unable to predict how the atoms moves. And then the second thing is that to integrate the acceleration into the position, we need to do a numerical integration, which means that we can only predict the change in the velocity after a very small time in increment. And so it means that we have to do these cycles many times where we predict the new position after a small time and then after a small time again. And the problem with that is that it takes a lot of time, so usually we can only predict for a few picoseconds or a few nanoseconds of dynamics. So what we're trying to do here is to replace this molecular dynamics algorithm with a machine learning model that can simply predict, by example, simply predict how the atoms move. And so the goal of this machine learning algorithm is to replace molecular dynamics. To replace molecular dynamics to be able to predict the motion of the atoms faster than what you can do with molecular dynamics. So this is how it works. So this is typically how it works with molecular dynamics simulation. You start with some atoms. Based on that, you predict how they move with this cycle that I just showed. And so here what we do is that we replace this cycle by a graph neural network, a machine learning model. So the way it works is as follows. So we start, for each atom, we define all its neighbors. So those are all the other atoms that are within this cutoff here. So this defines each of the atoms becomes some nodes, and each of the chemical bonds becomes some edges. And so this becomes a graph where you have some nodes that are connected to each other with some edges. And so once we have this graph, then we use this graph for a graph neural network, a message passing graph neural network, where the goal of this machine learning model is to predict how the atoms move over time. So we represent this structure as a graph, and then we make this graph evolve, and we teach the machine learning model how to make this graph move over time. And so the way it works in practice is as follows. So we start again with the position of the atoms. Based on that, we define the graph where all the atoms becomes the nodes and all the chemical bonds becomes the edges. And once we have this, then we do a message passing where we update the edges and then we update the nodes. And after that, we decode this message passing layers, and we predict what will be the new position after a small increment of time. So this is the graph neural network here. It predicts the same thing as molecular dynamics. It predicts how the atoms are moving over time, but it can do that faster than molecular dynamics. So a little bit more details about the machine learning model that we use. So we start with a given configuration like this with some atoms. Then based on that, we transform it into a graph. And after that, so we use this message passing, where we have first an encoder, so that converts the variables that we have. In this case, the variables that we have is two things. First, for each node is one atom. So we have a certain number of attributes for each node, which is the type of each atom, or what element it is. And then for the edges, the attribute for each edges is the vector between the two atoms. So if we have atom 1 and atom 2, it defines a vector that goes from atom 1 and atom 2. And the three coordinates of this vector becomes the edge attributes. So we take those nodes attributes and those edge attributes, we encode them with some artificial neural networks, and after that, so this transforms it into some latent variables, and we use this message passing to update the node attributes and the edge attributes with the message passing algorithm. And after that, we use a decoder, and at the end, what we get is this: we predict the change in the position of each atom and the change in the velocity of each atom, so that we can generate the new position of the atom after a small increment of time. So at the end, we get exactly the same as the molecular dynamics simulation, but this thing is just a machine learning algorithm, so it's faster than molecular dynamics, and we do not need to know the energy between the atoms. It can simply learn this by observing some trajectories. So here is how it works. So this this is a true molecular dynamics simulation. So this is how the atoms moves if you simulate this by molecular dynamics. And here on the right, this is the same. This is what is predicted by the machine learning model. And so you can see that the atoms, the true motion of the atoms and the motion that is predicted by the molecular dynamics model, it's a very good match, both in terms of the fast vibration of the atoms, but also a little bit longer diffusion here. So the trajectory, the true trajectory, and the one predicted by the machine learning model is very close. So the machine learning model is able to learn how to predict how the atoms move over time. So another way of seeing that is here. What I'm showing you is on the y-axis. This is the predicted position. This is the position of the atom that is predicted by machine learning. And on the x-axis, this is the true position predicted by molecular dynamics. And here it's the same for the velocity. Y-axis is the velocity predicted by machine learning, and this is the true velocity predicted by the simulation. And so here what we expect is that we have a pretty good match. Since everything is on the y equal x line, it means that the predicted is very close to the true position, and the predicted velocity is also very close to the true position. So altogether, we're able to predict the position with an accuracy of 0.03, where here the size of the atoms is equal to 1. So we are able to predict the position with an accuracy that is much smaller than the size of the atoms themselves. So then we tried to look at this for different systems. So we simulated 3 types of materials here. One is a silicon liquid, one is a silicon, and one is a copper zirconium. And so these 3 systems have 3 types of difficulties. For example, in silica here, you have some long-range Coulombic interaction. It's made of cations and anions, so you have some long-range Coulombic interaction. Then for silicon, you have some free body. You have some angular constraints that maintains the angle between the atoms. And then for the metallic system, there is some many body interaction. So there are 3 systems with 3 different levels of complexity. And so for each of those systems, we do the same. We first train the machine learning model to learn how to predict the motion of the atoms in those 3 systems. And then we check for some new initial position if the machine learning model is able to predict that correctly. So this is how it works. So again, this is for the 3 systems here, a comparison between the dynamics of the atoms predicted by molecular dynamics and the one predicted by the machine learning model. So in each of those 3 cases, the trajectory predicted by molecular dynamics is very close to the one that machine learning predicts. So again, like here we have this machine learning model that can replace the molecular dynamics and directly predict the atoms faster than for molecular dynamics. So then, like one thing that is important is that we need to be able to do that faster than simulation. So one advantage of this molecular dynamics model is that it's not necessarily limited to predicting the motion of the atoms after one time step. It can predict the motion of the atoms after 10 time steps or 20 time steps. It can predict the motion of the atoms more in the future. So that's what I'm showing you here. What we did is that rather than training the machine learning model to directly only predict what happened after one time step, we directly predict the new motion, the new velocity, and the new position of the atoms after a certain number of time steps. And so this allows us to save time, where we directly predict what happens a long time in the future. And so based on that, we can accelerate those simulations by replacing molecular dynamics by machine learning. So this is a comparison here of the computing time. In black, this is the computing time if you just do a conventional molecular dynamics simulation. And here in red, this is the computing time if you replace this by machine learning. And here the x-axis is the size of the systems. And so what you can see here is that for each of those three systems, the machine learning is much faster than the molecular dynamics simulation. And the more you have a large system, the more it becomes faster and faster. So this shows, like, especially for systems like this that are very complex, the speed up that is offered by the machine learning is very significant as compared to the computing time that you need with molecular dynamics. And one thing that is important is that if you compare the computing time for different systems, here what I'm showing is the time to perform the simulation for the different systems that we had here as a function of how complex this system is. And so what you see here is that the more the system becomes complex, the more molecular dynamics here in black takes longer and longer. But for the machine learning model, the computing time is very constant. The computing time with the machine learning here in red, it doesn't depend on the complexity of the system. It just depends on the architecture of the machine learning model. So if we use the same number of layers in the artificial neural network, this computing time is very constant. So we can simulate very complex system with the same computing time as a simple system. And here all of these comparisons are with classical molecular dynamics. So if you were to compare with ab initio molecular dynamics or DFT, then DFT would be like even like orders of magnitude more expensive. So we would have even more speed up there. So yeah, here are a few conclusions. So the first thing is that here what we are showing is that machine learning can directly learn to predict the position of the atoms simply by observing some trajectories. So the way it works is that you first do a certain number of simulations. Then you take those simulations, and the machine learning will learn from those simulations, and then is able to predict for new initial position that were not included in those examples that you provided to machine learning. Now it's able to predict how those atoms are going to move over time. And so one important thing is that the accuracy of this machine learning is very good. It doesn't depend on the complexity of the systems. You can simulate more and more complex systems, and the accuracy is still good. And one thing that is important, eventually we want to use that to be able to do longer molecular dynamic simulation or larger system. And so that's what is enabled by this machine learning model. You can do simulation faster than if you were doing it with molecular dynamics. And a couple of more thoughts here. I think one thing is that machine learning usually is used to more informed simulation. For example, you can use machine learning to parameterize force fields for the atoms. But here the idea is that now we can really use machine learning to completely replace simulation altogether, and this is really what allows us to save a lot of time and do longer simulation, simulate larger systems at a fraction of the computing cost. And so one thing is that this means that you can use this to replace classical molecular dynamics, but if we were to also do that for density functional theory, then it would be even more speed up. Like we can, again, do some trajectories with DFT, with ab initio molecular dynamics, then use machine learning to learn from those trajectories and then replace DFT by machine learning. And so it's also a little bit more general than that. Like here, the idea is just by machine learning doesn't know anything about the Newton's law of motion in this case. It can directly learn the Newton's law of motion and learn the potential energy between the atoms simply by observing some trajectories. So this is more general than that. It can be applied to other types of n-body system where sometimes we don't know the constitutive motion, the constitutive law. So whenever we have an n-body system like this where we can only observe trajectories, but we don't know anything about the constitutive model or the governing equations behind these types of systems, then we can use machine learning to observe those, how the atoms moves, and based on that make some predictions. So yeah, here's a reference if you're interested in this work, and thank you for your attention.
네, 질문 받도록 하겠습니다. 질문은 영어로 해주실 수 있으면 좋을 것 같고요.
Thank you very much for the great talk, Professor Bauchy, flying all the way to Korea to give a great talk. So I've got two questions. The first question is, I'm kind of wondering if error can accumulate over time, and maybe will diverge to a configuration that machine learning model does not understand, and maybe machine learning tends to explode when it's not in the region that you can predict well. And second question is, so I understand that the time speed up is very good when you are just making a prediction to single structure configuration. But I guess the purpose of the MD simulation is to perform simulation until you get the set of equilibrium configurations and so on, right? But how much training set do you need? If you need training set that includes all the structure to the equilibration, then I don't know if there's really any speed up when you're looking at the whole picture of using MD. So those are the questions.
Yeah. So for the first question, so as you say, every time you make a prediction using machine learning, there is a small error on the position. So after some time, the trajectory from molecular dynamics and the trajectory from machine learning, they will start to diverge from each other. But this is the same as if you just do two molecular dynamics. You will get slightly different result because of small errors that accumulate over time as well. So we are able to predict about for 100 steps. After that, the position changes. But our goal is not just to predict the exact motion of the atoms. Our goal is more to predict some properties, like for example the diffusion constant or the viscosity, and so the position maybe diverge, but the property still remain the same. So that's one thing. For the cost comparison, so yes, you are right. You still need to first do some simulation to train the machine learning model. So I think it depends on what you're trying to do. So if you are here, those simulations, they are at equilibrium. It's just a liquid, so it's not evolving over time. And in that case, you don't need that much training. You just train the machine learning model based on a certain simulation for the liquid, and then it can predict the trajectories for other liquids. We can still do that at different temperature. For example, one result I can show you is here. What we did is we trained the machine learning model at a certain temperature, and then we were able to use the machine learning model to make some prediction at other temperatures. So you can train at one temperature, but machine learning will still work at other temperatures. So it's still able to extrapolate a little bit outside of its training set. But yeah, so if you, as you said, if you have a system that is changing over time, then if it's changing so much that it becomes very different from its initial position, then machine learning model would not be able to guess what would be the dynamics of this new system it has never seen before. So you would need to retrain the machine learning maybe by active learning, where as soon as you realize that the machine learning model doesn't know what to predict, then you need to dynamically retrain the model as you go. So yeah, I think the level of speed up, it depends on if you have a model, if you have a system that is really changing a lot over time, you would need to include the retraining to see if there is really a speed up or not.
네, 저희가 시간 관계상 더 질문 받기는 힘들 것 같고요. 네, 질문 있으신 분들은 나중에 세션 끝난 다음에 연사분께 더 질문해 주실 수 있으면 좋을 것 같습니다. So it was a very nice presentation. Let's thank our speaker again.